The BSides DC 2017 videos are brought to you by Threat Quotient, introducing the industry's first threat intelligence platform designed to enable threat operations and management, and Data Tribe, a new kind of startup studio co-building the next generation of commercial cybersecurity, analytics, and big data product companies.
Hands, who here knows P&MP? Okay, I got a couple. Okay, this is going to be fun. Because my background's in large-scale data analysis, cluster computing, high-performance computing, making things work. And I backed into security about 12, 15 years ago. So I'm coming at this from that lens. And this story is sharing with you the things that we've figured out as we've been trying to move around big pieces of data, and leaving you with some of the first principles and the key elements that we focus on when we try to solve the problems. I'll talk about some of the stuff we're finding, but for me, the really hard part is how do you actually carry around 1 trillion records, and how do you make it useful? So you go to DEF CON and there's like 2 talks. There's like the one really cool talk where the guy hacks a satellite. Everybody seen that talk? Okay, I got a snicker, that's good. And then there's let me tell you a story. I'm a let me tell you a story guy. And the title of the talk is Adventures with Trillions of Records. And so every adventure starts someplace. And every analytic or useful analytic exploration starts someplace. And my argument is we got to start with a problem. I've got 1 trillion records isn't a problem. It's an opportunity to geek out for a while. Here are some problems. You have to think about why we're looking at the data, what question we're trying to answer. It took me about 10 years of getting my soul broken by my bosses before I realized it just wasn't enough to answer a cool question, because that cool question actually did nothing, but it was a cool presentation and it was fun. And so none of these actually have much to do with TCP or servers or any of that. A buddy of mine is out in Seattle, and he keeps talking about presuming you're going to get hacked. You know, everybody gets scanned every day, Cat 5 hurricanes. Which are the attacks you should worry about? Which are the ones that are actually getting close to the stuff that is core to your business? He runs an educational institution, so he worries about making sure labs work and students' PII doesn't get stolen. At my church, we've got the people who go there, we've got the employees, and we've got the PCI information so we can donate. And that's about it, right? This is the core infrastructure. If the Wi-Fi goes down in the church, nobody really cares. But we got to start with something that's not 1 trillion, that's not how cool is it to carry stuff around. And then we start talking about the data that we apply to it. The groups that we work in, we not only look at large amounts of data, but we look at many different types of data. My AI professor pointed out that bias is good. And it's good because otherwise you have a huge undirected search through multivariate space that you're wasting lots of CPU and people time, not going the place where our gut, everybody in the room, knows kind of what is hinky. That bias also tells us the data sets we should pull together. If we're doing insider threat analysis, there are some things we actually don't care about. If we're doing external exposures analysis, there's a completely different set of things we care about. The reason CVE and CPE are up here, besides they're in one of my favorite graph formats that we'll talk about in a few minutes, is they give us a common way across data sets to represent technologies and candidate threats to those technologies. Defense in cyber is a team sport that requires everybody to play the same way. Unfortunately, that's impossible. It's the opposite of the NFL, where you just need one guy in the right place at the right time to blow the whole play up. Unfortunately for Bill Belichick right now, he's suffering a little bit because he's not having a good defense. We're unfortunately the 2017 Patriots currently in cyber. Offense, consequently, you need one guy in the right spot at the right time. And so what we end up doing is not saying, this is the attack that's going to get you, but saying, this is the coalescing or the gathering of the energy that represents the highest amount of threat. Security is a risk-reward trade-off. Anybody else here run into the problem of don't turn off the boss? Nobody? Okay, cool. Again, apologies for being a revivalist preacher. This is a problem where you see this mobile device coming in to check webmail. It's on 3 p.m. on a Friday. You turn it off, it's awesome, and about 10 minutes later you get a phone call because the boss was on the golf course and he was checking whatever his important email was as he was getting ready to do a deal with the guy he was on the 6th hole with. And all of a sudden you stop the deal. And now instead of being a hero, you are actually just going to get kicked in the teeth, right? And that calculation of where's the risk-reward continuum is exactly what plays into using the CVEs, for as good and bad as they are, as a representation of available technological risk and mapping that back to resumes and technical indicators that you've got about your organization. There's no sense in hunting, trying to patch things that don't exist in your world. There's only sense in trying to patch the vulnerable technologies that you actually have running and are actually externally visible. Okay, so now that we've got an adventure to go on, we've set a couple questions, we've got a set of data to pull together, we can just search for something and we'll be done, right? This will be good. It doesn't work that way. And the reason it doesn't work that way is every data set is different, just like a special snowflake. When you get a data set, you actually have to measure it. You have to understand what the diurnal patterns are in it, if there are any. You have to understand what the weekday, weekend, you have to understand which holidays you're keeping. You have to understand kind of just how big is it on an hourly basis. All of these things together inform the bias that we talked about 2 slides ago. You need to make sure the biases you've got in your head are the same as the biases present in the data sets. I was chatting with a team that I'm friends with, and they had just turned on DNS monitoring, and they were getting all of these DNS tunneling alerts off of this appliance that they plugged in. And they were all getting ready and getting excited because it had critical vulnerabilities and big piles, 30,000 over about 4 days. And so they actually bothered to talk to the guy who helped them plug it in. He's like, oh yeah, that's because of the way that you've got your redirection set up in your network. They didn't look at the alerts before they started to get ready to call the cops on them. They didn't perform sense making on their data sets. We also call this exploratory data analysis. This is one case where it is completely okay to ask wacky questions. You want to know the foibles about your data. How tall is it? What is its 40 time? All of that craziness, because then you know what are the questions you can actually ask of it. And if you don't go through that stage, at best you're getting lucky, and at worst you're reporting on benign signal and you're wasting people's time. Okay, so we've got a question. We've got some data. We're getting ready to sense make it. But we need to use the right tools both for the sense making and for the answering of that question we said at the beginning. And these tools are different. And the tools depend on the size of your data. Anybody here good on sparse matrices? Cool, okay. The reason this matters is 6 degrees of separation is very real. There's this thing called Zipf's law. It's present in almost every element of natural behavior. The vast majority of human activities, or actually cell pairs in strain of bacteria, et cetera, are dominantly the same. And the long tail is where you get a lot of very useful information, or Shannon's entropy. Okay, so why does this matter? This matters because joining the data sets, as you bring the right data sets together to answer your question, becomes a computationally difficult problem. Dense graphs, ones that are not Zipfian, negative power law, are a well-filled in matrix. They are well represented by ones and zeros just in a table. Sparse graphs, which are called small world graphs or negative power law graphs, are what we find in LinkedIn, on your network, the way that your clients and servers interact with each other, the way that my clients and servers interact with each other, the way that you interact with the internet. The Alexa 1 million is interesting because after you get out of the top few, then you're getting into really weird behaviors that are highly discriminating. Technically, the way to do that merger is not through SQL, because SQL is built to do financial analysis. So the key tool that we all use started as a mainframe program so that actuarials and accountants could add up sums and do arithmetic. There's no bearing in those numbers and the underlying patterns in them to the underlying mathematics and organization of human behavior. So the fundamental computation that SQL is optimized for actually slows down the exploration process. Because everybody here has tried to do a left join and then pound your head on the table. Like, it just doesn't work. And above about 3 joins, you're looking at an NP-hard problem. Matching across multiple data sets without a primary key is a pattern match. When we transform this into a graph world, that becomes NP-hard. It's called a subgraph isomorphism. Well, the way you cheat on that is that you keep everything in memory. And you represent everything as a graph. So instead of representing things as matrices, you start representing things as lists. And you can iterate through ordered lists in constant time. And you can find the joins and start walking it through. Being in memory is 100 times faster than being on disk. This explains the difference between Spark and Hadoop as computing platforms. So when we combine the difference in the representational model and just using RAM like it's going out of style, we get a lot more performance. And that's kind of fun. And that performance becomes really important because the most expensive thing we've got is all of our time. There's a reason BSides is on Saturday and Sunday. It's because we couldn't come otherwise, right? I was in 2 cities this week and my wife still doesn't like me. We travel too much, we work too much. We're using our spare free time to do this because our time is too expensive. So we shouldn't use platforms to do this exploration that are not designed to be most efficient of our time. A few of the design principles we've learned is that the time to prototype an idea is that clock time is the most important thing. Because if you only got 20 or 30 minutes to analyze a problem, that's the amount of time you have to discover something. To learn something, to identify something that you say, hey, that's kind of cool. I should give this to my other analyst who's got another 30 minutes so I can keep the ball rolling. And so you can make technical choices in engine type and in data representation that make putting in new data sets really easy. In any database, we've got a trade-off between density and flexibility. You can hand write C++ representations to represent something like NetFlow. And if you work at it kind of hard and you're a little smart about it, you can get it down to about 24 bytes. That's awesome. But it can only take NetFlow. And if you want to merge it against a different data set, it's going to take 3 to 10 days of a really good programmer writing a completely new data structure and looking at the merge. If you're willing to sacrifice and look at 500 to 700 bytes a NetFlow record, you can put it into an XML-like format that gets you a lot of flexibility, that makes the merges easier. And the reason we want to make the merges easier is bias is good, because bias tells us which data sets we should put together, and how we should down project the data from multiple dimensions into 2. And this forms what's called a joint distribution, where you've got one data set or one feature on this side, one feature coming up this way, and an XY plot of all of the data in these 2 dimensions. And if you choose your dimensions well, you end up with this really cool thing happens that makes you feel really dumb, is that you've got these outliers here that you say, what the heck is that? And then you start this exploration process over again on that cluster. And the speed of putting data together so you can ask that question, get that representation, and start that cycle again is what we call a time to second solution. So I've done it once. Let's do it again. Hey, I had this cool idea. Can I do it over again? And then the key metric is how easy is it for us to spin up more people? I don't know about where you guys work, but where we work, we never have enough people. Yeah, right? And they said, oh, well, just make more of you. I'm like, okay, no, nobody wants more of me, right? And B, if you take the crucible that got me here, you can never recreate it. I started in 97, 98. The world's a lot different in the last 20 years. The speeds are different. Now these things called cell phones actually do a lot more than that does. All we can do is get smart people and put them into an environment where they can go through some of the growth process we did, hopefully with less side trips that were unproductive. There's millipede development and grasshopper development. And I'm going to make a martial arts reference here in a second, but it has nothing to do with grasshoppers. Grasshopper development is, hey, guys, we've got $40 million. We're going to do this great thing. We're going to be so awesome at cyber in like 3 years. Yeah. OK. So you take this big leap, and you jump off the stage, and you got Superman legs, and my son's so proud of me, and I misjudged, and I hit that exit sign over there. I didn't go through the door, right? Kind of got a bloody nose. I wasted my superpower, didn't catch any bad guys. Or I can walk off the stage. The agile cycle doesn't just feel good, and Scrum Mastery isn't just a thing we put on our resumes. It is actually a better way of doing analysis in this experimental world. When you can actually ask questions and get answers back in seconds to minutes, you can mature your way of thinking and accelerate that process of growing people by forcing them to make decisions. Okay, so I'm going to ask another question. Anybody here got an MBA? Wow. Okay, so my wife does. She's super cool, makes me look like I am really flighty. And what she taught me going through her MBA, besides the fact that it's a 40-hour-a-week job on top of your 40-hour-a-week job, is it's 100 business use cases. It's 100 small decisions. It's 100 examples of choose something now. And what they're trying to do through the use case model is the same thing we actually all do, which is here's a problem, try to solve it, know you're wrong. Driving bias into people. There's some MBA programs that you stop and you do them for a year and a half. And that's all you do, and that's fine. There's some programs that you do it over 17 or 18 months, and you do it evenings, weekends. It's about the compression of decision-making cycles to force you to learn, to force you to accurately sample the underlying feature space, which is good and bad decisions in business. We've got exactly the same problem. How do we get new people on the team? How do we make them productive members of society? And the trade-off for us is we cheat 2 ways. Yeah, exactly. No, that's a good snicker. We cheat because we give them languages that are very easy for them to use. Because that's what we want. We want them to be interacting with the data and accelerating that growth process. So we give them things that are either SQL or look very much like SQL. So you're going to say, hey, Eric, you just told me SQL is bad because it's got underlying table representations that are really dense and aren't appropriate to Cyber. Yeah, that's because there's a SQL for graphs, and it's called Sparkle. It's an open standard. It came out in 2001. I don't know if the rest of you noticed, we're still not in the semantic web nirvana that we were promised. But Sparkle is like the one thing that hung out after that. Sparkle processes RDF and does pattern matching natively. Cool. Well, CVE and CPE already come in RDF. DBpedia already comes in RDF. So you can kind of get all of DBpedia either through a web API, because there's this thing called a RESTful Sparkle endpoint that you can give Sparkle to, and it gives you an answer back, which means that you can use itty-bitty Sparkle or RDF engines, or really big ones, depending on how much data you have because you did your sense making. So now you have a way for your analysts to do native merges of their data sets using a language like SQL. Because it is RESTful, we can embed it in Jupyter notebooks. This is really, really handy because it helps us crystallize people's thinking as we're growing them up in that forge, right? As we're helping them mature. Because by giving somebody a Jupyter notebook with an analytic workflow of how do you actually evaluate this type of IDS alert, well, you drop it in here, you get some not really attractive but highly information-dense tables back. You look at it, you find the breakpoint, you put it in, you keep running. You ensure that the only thing they screw up is making the important decision. They don't screw up where the equal signs are. They don't screw up the query itself. Instead, now Jupyter notebooks become this handy thing that you could hand around. You can put under source code control. You could actually instantiate knowledge into people. Which means that then we've got Python in the Jupyter notebooks, which means our data scientists can start to go crazy without actually bothering people with words like non-parametric goodness of fit or Zipfian. Like, you guys are really nice to listen to me talk about negative power law stuff. So you jam these teams together where each of them knows how to contribute to a Jupyter notebook and sit around and have a beer and say, this is what this means, so we can answer one of those questions we decided on at the beginning. Okay, so I said trillions, right? You guys are all waiting for the big payoff pitch. So I'm going to let you marinate on that, on this number. I've got a friend who's got a network who's got about 250,000 things on it, who put the stuff, who rebuilt their layer 3 so that they could get full east, west, north, south net flow. That's kind of cool. They average about 250,000 net flow records a second. You can do the sums too. 7 trillion is a lot. Good news is they're collecting this because they know they have questions that need to answer this. They just don't know how to answer them yet. And that's a scale that makes me a little nervous. And I'm the crazy guy who's been spending my life doing HPC. Scale comes in density, or in just transactional volume, and that's about 95% of your record set when you start looking at a corpus. Your credit card transactions, for instance, are just transactions. They're highly structured. They come in repeatedly over and over and over again. You know exactly what they're going to look for. About 4 months ago, I got this phone call from American Express at 10:30 at night. Nothing ever good happens when American Express is calling you. I know Wells Fargo calls me all the time to tell me about my credit card debt. I don't bank with Wells Fargo, but I actually work with American Express. And so they called me and they said, guess what? You're shopping at Walmart.com. And I said, I'm going to bed. Because I legally know that I am out for $0 on this one. And the next morning, the folks who had gotten their hands on my number had gone to HotTopic.com, to Walmart.com, and then to some no-name gas station and run up $85 with a clone card. Cool. The way that American Express found that had nothing to do with the transactions themselves, necessarily. I don't reliably go to sleep at 9:30 every night, just most nights, so they can't just use time of day. What they use are what we call enrichment data sets. It's all of the stuff that brings context to the table. And it's what we use to reason about whether this NetFlow record is okay, sort of okay, awful, or I should pull the plug on the network. We do the same thing with our credit card statements. And so when you're doing data analysis at this scale, you've got 95% of your data set is transactions, and 5% of it is everything else. That gives you that context that you bring in with the bias that helps you answer the questions more efficiently. So I've got a handy triangle here, and this is my answer to everybody who says, oh, we should just use machine learning and it'll predict the bad guys and then we're done. Do you guys hear that too? Fantastic, we found an answer. Okay, it's an utter fallacy because there's published research, most recently by Vern Paxson and Ethan Summer out of RAID 2010, that says outlier detection in anomaly detection doesn't work because the false positive, false negative rates are too high. Why is that, Eric? Well, I'll tell you. The reason it is the multivariate space is so high. There's so many dimensions to an IDS alert that machine learning works off of oversampling the underlying behavior in each of those dimensions. Because there's a continuous curve or a discontiguous curve and pockets of good and evil all through this 25-dimensional space that looks like Swiss cheese. And you have to have enough examples of good or bad to actually identify with discrete points where the good and the bad are. And if you're sufficiently undersampled, you don't even know what some of the dimensions are, there's no way that machine learning is going to get anywhere close to doing anything but getting you fired in about 3 days. Because after the first day, you're going to be like, no, boss, I got this. I just set the knobs wrong. After the second day, you're going to look a lot worse because you didn't sleep overnight because you were nervous about using machine learning improperly the first day. And then by the third day, you will just have handed in your paper because you've shut off the guy on the golf course too many times. So you have to start at the bottom. You start with 1 trillion records first. And then you search them. And for some people, that's grep. And that's okay if it's fast enough to help you answer the business problem we set out at the beginning. If you can't search the data, just delete it. Unless you need to have it for a retention requirement. But if you cannot search it, just be super upfront with your OGC and your legal folks when they come to you and say, do we have evidence of blah? You say, I don't know. The data is unsearchable. I have a team that I'm friends with who said, we had an event. I'm like, okay, events are bad. And this event, we've got the data that can tell us about it. I'm like, okay, that's a step in the right direction. And we know we have the data. Okay? And they said, it's taking us a month to get a return off of one query. Said, okay, so the Earth's crust is going to cool before you actually analyze your event, which means that the 178 days or whatever is in the Verizon report, you guys are well behind. They can't search it. And they told somebody they had it. Context is that handy thing Google gives you in that little snippet. It's that stuff we carry around in our head, so when we look at port 23, we know we don't want that on our network, and port 21 is worse. It's summarizing the data in a way that is informative to our analysis process. And so once you can do searches, you start pre-thinking about the next search you want to do, and building those tables ahead of time is the contextual piece. And once you start doing the context well enough, then we can do outlier detection. We say, hey, wait, that doesn't make sense. We understand the context so well enough to highlight this automatically to show to people. And then you can do change detection. My diurnal pattern changed because I had a good enough definition. I know that the number of mobile devices on the network fundamentally changed because it went from here over to there and then stayed there. There's this thing called a threshold random walk, which is also known as sequential hypothesis testing. Vern Paxson, who at this point I've referenced twice, so you can tell I like him, he wrote a really nice piece of math around using sequential hypothesis testing to identify port scanning based on the relative frequency of successful and unsuccessful TCP connection attempts in your network. Well, the good news is that this same math works, and this same process works for any event stream process. And as soon as you can put good evil bounds around how frequently should this behavior be happening, and if it's not happening at that frequency, start counting. Because all a sequential hypothesis test is, under the covers, is a number of steps one direction or another. If you make the number of expected steps you should have about 4 or 5 in one direction, hey, I'm benign. This is expected behavior. Cool. Well, being paranoid, cynical grown-ups that we are, that just means we start running the test again. Because the next 5 or 6 events could be the ones that show us that something bad has happened. Conversely, if you have 5 or 6 steps in the wrong direction, 5 or 6 is actually defined in the paper, then you know something bad's happening. And you keep watching it to make sure that it stays evil while you call the cops and get paged at 3 a.m., et cetera. This is a very simple, non-parametric, which means we don't actually need a model. We can use past behaviors to set the good and bad thresholds, and then just run this. It gets a little fancier, and that's about all it is. You just need enough statistics to do that. Cool. That's how you do change detection. And once you've done all of that, you've got a well-defined analytic problem. You've got the data pulled together. You understand the underlying behaviors with a reasonable likelihood. Now you can do what's called classification, which is a fancy way to say, I think based on this set of attributes about this data point, this is whether it's going to be good or evil. And there's where you start getting your blinky red light. You can't do that for everything on your network for all behavior, because the underlying feature space is so big. You can do it for things that you understand well enough that you can give the system an expectation of thumbs up or thumbs down, to use a rating system-like analogy. And so this gets into one of my rants on AI. AI is traditionally used for a fast thing. Is this a bad DNS query? Is this a bad host name? Is this login good or bad? Cool. That's a good application. But that fundamentally won't actually help. That'll help us do some automation. That'll help us catch some of the underlying bad guys. That won't help us have intuition or use the computer to start with intuition. And this is where I believe AI is most applicable to the field that we're all in. Because AI can do large amounts of unsupervised machine learning. So I just threw a new term at you. The difference between supervised and unsupervised machine learning is supervised machine learning, I have a really good label space. I know if this is good or evil. I've accurately identified my 25 dimensions. Unsupervised is, hey, where are the hills and the valleys? Where are the clusters? And by being able to express your underlying data set in that way, you can then start saying, do I believe these clusters should exist? Watson playing Jeopardy is an example of what I call slow speed AI. It's asking questions. Now, it was trained to ask questions, and I had a whole bunch of data. But here's where we can use large amounts of machine learning and large piles of data, at the trillions level, to say, did I have new connections show up? Did I have a new port bubble up? Is there a change in the underlying bias that I can highlight? So in those 2 hours Friday afternoon, while I'm, depending on your organization, having a beer or thinking about having a beer, and you've decided that your to-do list is done enough for the week, and you actually unclench your brain, and you start having these really cool ideas that, for me, depress me, because I'm going to mostly forget them by Monday, or I know that we won't have time to do them. But in that time, we should be looking at the weather on our network and how it's just fundamentally changing. I'm a big hurricane nerd. I'm also a snowstorm nerd. So the NOAA's National Hurricane Center website is the coolest thing ever. We should have the same thing for our networks. One of the dominant questions I get asked is, how many connections do I have? How many physical connections do I have leaving my network? And I'm like, you don't know? Is anybody here willing to state with certainty they know how many they got? Right, nobody puts their hand up because it's your network and you still don't know. I've got one client with 47. They're global. The only thing they know is they don't have coverage on them. That's a problem. How do those look? How are they changing? Being able to understand the underlying behaviors so that you know what a bump in the night sounds like, that's what we should be using things like prediction for. Not saying this DNS thing is more likely to bite me in the tush in about 3 days. Okay, I gave you some bullet points to think about. It mostly comes down to really good fundamentals. I don't know if you've tried to SCP a terabyte of data around. Right, okay, exactly. It's easier to fly a pimply-faced youth, for all of you who read the register a long time ago, put them on a plane, send them down with a hard drive, get them to bring it back. Yeah, we actually do that because it's easier. Why? Because data's heavy. It's better off to make fundamentally good decisions once or twice about where you put it and the tools you put over it, using some of my considerations on the last slide, than saying, okay, well, the first thing we're going to do is we're going to build an awesome data lake, and it's going to have all these channels, and it's going to be like the Netherlands, and it's got this great technology, and we're set. Maybe. If you've got farmers like the Netherlands, make sure you're using the right representation for the staff so that your team can ask the questions. Because otherwise, we're back down below search. We've got data that we're paying EC2 money for, or any other cloud service for, that you don't know what to do with, and you physically can't do anything with. Remember what the question is that you're asking. I am guilty of nerding, in case you guys haven't figured that out by now. This means I think that things in data are really, really cool. You guys do too. Otherwise, you wouldn't be spending your Saturday walking around here listening to mostly interesting people talk, right? We all want to go down rabbit holes. That doesn't answer the underlying security questions. We use a lot of partial summarization called question-focused data sets, primarily to pre-summarize the data and use bulk compute for what it's really good at. Turn lots of those transactions into something slightly smaller that's easier to handle. You're like, okay, that's pretty cool. And we would get to a point where one of our guys would run something, and he'd reduce 1 trillion down to 1 million, and he put 2 thumbs up, and he said, I won, and now I'm going to pull it off of that big beefy server, and I'm going to bring it down to my laptop, and I'm going to run a 1 million row Excel spreadsheet in my laptop. We're like, you just gave away 128 gigabytes of RAM. You're so stupid. And I still love them. Don't move the Excel until you're ready. Change all of your thought processes around where's the most computationally efficient place to answer the question. And that building blocks approach is really important. It's really easy to pull together a bunch of data, to bring it, to make it into a pile, to make a sandcastle, to win the sandcastle competition, and then the tide comes in, and then you got to build another one. Did you actually automate the way you built the last data set so that the next one is exactly the same as that one, so all of your same sandcastle building stuff works? Usually not. That's okay. We all hack it up. Try to force as much rigor on yourself as you can when you're building your subsets of your data to get the benefit of learning from the first time. And then plan for asking the next question. Because as soon as a prediction thing happens, you're going to start searching immediately. Because now you've got a new thing to ask questions about. The reason I've got this brace down here on context and search is that's about where 90% of your questions get asked. They're small questions. They're generally not big computationally complex questions. They may take a long time to answer because of the scale of data and the nature of the engine you put them in, but you're going to ask lots of them. You don't ask very many big prediction questions, but that's where you spend most of your computational time. Don't expect that flops put in is directly equivalent or sometimes at all proportional to the analytic value you get out. I'm working with some friends, and they've got an event. That's exciting. And we were given about 85,000 IP addresses, and they said, what can you tell us about these? And we said, well, we could actively scan them if we can get permission and OGC and legal. We could go to Shodan or Nmap or something similar, Zmap, because that's fun. We could just ask our passive and reverse DNS resolver. So we did. And as dumb as that sounds, we looked up 85,000 IPs and built a spreadsheet. And we handed it off to the guys doing the day-to-day triage. And they think it's amazing. Why? Because they don't have to go to another tab in the web browser. Because they've got just a place to ask a question. Okay. So what are some of the things that my jumping up and down and waving actually helps find? We don't do signature-based stuff. There's lots of tools that are really, really good at that. The technology for doing pattern match that way is well-defined. We hunt the invariance in the behaviors and then depend on the enrichment from the additional data sets coming in to give us that context, to help us find the things that are worth people spending time on. And we also try to focus on the things that are most important. We don't try to focus on affections coming in, because you've got lots of technology that does that. We spend the majority of our time focused on what's gotten through that. What has gotten all the way through your stack and now looks like it's doing something like beaconing. That looks like it's doing something that's starting to exfil. An exfil and a download and an upload into a cloud hosting service are identical. The only difference is the scale, who we think might be doing them, what time of day it is, a number of things that indicate it violates expectations and is worth a person taking a look at. We keep people in the loop on 99% of our analyses because we know that we don't know what we're really looking for. But we can reduce 1 trillion records down to enough that somebody can take a look at it and make actionable decisions. This interactive traffic over web ports is some of my favorite stuff, actually. Just because it highlights that the more people try to be sneaky, the more obvious they are. There was a paper that came out a year ago at BroCon around detecting SSH brute forcing. And This is cool. Like, they showed there's a piece of machine learning that's fast machine learning that does this. There's math that does it. It's now in Bro, actually, that it'll detect SSH brute forcing just from the nature of the connections, their speed, and the number of packets that are in them. You can determine empirically how many possible packets there can be if you go through all of the authentication methods and get your password wrong 3 times. Or wrong twice and right the 3rd time. If you have a session that is more than that, it is established. And somebody dropped you a prompt somewhere or is doing an SCP. Cool. And once we can identify those, we then have elements of the packet stream that are directly indicative of whether it's interactive or a bulk upload or download. At that point, you've got an interactivity detector. It detects things that may or may not have push set on the packets, but are not acting like web or any other bulk thing. Now, there are lots of things that should be running on your network. And there are lots of interactive things that should be running on your network and that should be going in and out of your network. And indeed, we all use TLS encrypted things to talk to our buddies outside of our network. And this is where that enrichment data comes in, because as soon as we can identify the interactivity and we can whitelist out a number of those things, it's then what else is running that shouldn't be running. It allows us to say, this is normalcy for interactivity. What's the weird stuff? Which is what we get excited about and where the really evil bad guys are. So what? We've still got a data merge problem. The hardest thing we've got is not a math problem. I mean, you and I can have a chat over a beer and I can give you the 3 references that give you all of the math that you could possibly want to go implement. You've got a visibility problem. I know I've got one set of buddies who have good coverage and good visibility. I know a whole bunch who don't even have the metadata to be able to answer the question of what happened. These techniques are ones similar that I used on a bunch of incomplete ACLs several years ago. Something happened, somebody gave us a call and said, here are 1,600 ACLs, what can you find? And we found lots of interesting things doing exploration. We found that the sysadmin was a high roller in Vegas, actually, which was kind of concerning considering the amount he was getting paid. And we found that because the website he was using to book his hotels used open source clear text passwords, and we saw them in the post. That was kind of exciting. And then we found other evidence of beaconing that weren't supposed to be there. We did it on 1,600 ACLs, nowhere near a complete set. And this is where I try to leave you with a moment of restorative hope. I just talked to you about a bunch of theory. It's practical theory, but it's not something you go buy in a box. It's a way of thinking. I told you that I give you a martial arts reference, and here it is. I've been training for about 10 years. It's annoying. I don't want to get up in the morning. I go to the dojo every day. I have really good people kick my ass. I go to work. And yet I still keep doing it. 1, because I'm incrementally getting better. 2, I look good in a pair of hakama. Let's not lie. And 3, the dojo is a forge. And it is a reflection of what I bring to the mat. And I am making myself better. I'm refining myself and the way that I think through getting thrown around and trying to hit people with swords, etc. It's all mental. So these principles that we've talked about that are hard can serve to guide us in that maturation process as we bring new members of the team on to help them grow and mature so that when we are doing analysis, it is like being at the dojo, where we make sure we execute correctly when we do analysis, so we get better at analysis. We're paranoid and we're cynical because they are out to get us. We're also paranoid and cynical because that's the way that we've learned we have to be with the data sources we have. And the threat behaviors are well in excess, well ahead of the things that we have tools to see. So the only way we bridge that gap is by training ourselves to ask better questions and to perform better all-source analysis very rigorously. I've got a buddy who works for a big software firm that gets crash reports in. Crash reports are really, really cool. Okay, so about 60% of them are not cool. They're video drivers crashing. Fundamentally uninteresting, and I was that guy once. I'm gonna date myself. I played Unreal in college, and I wanted to get the two cool video cards and put the cable between them, so then they do the interlacing. Yeah, I was never that good. What would?
Crossbar and SLI.
Exactly, right? The Nvidia. Okay, yeah, I'm old. But the point of this is, fuck. I didn't say that. I'm really sorry. Forge, learning better, whatever. We'll come back to it if I remember it. Oh yeah, and the other two things, plan for operationalizing what you find. If you find something really cool, it doesn't matter unless you can actually change behavior on the network. Oh, okay, so I remembered what I was saying about the software guy. It just took me a second. And so then they find other fun things that are happening. And they just get these crash reports. And for them, the fun part of it is looking at the piece of malware that's only ever seen once or twice. I'll let you hypothesize why that might be the case. And so the guy was telling a story, much like I am now. He had much better graphics. I only had one. And he's saying, okay. And we kept our eyes on the open source research. And we saw about 6 months before the open source research was getting close to finding this particular 0-day, it was used to hack a large organization for significant impact. Before that, it was used 3 years earlier once, the entire way around the world. They used the crash report to say, hey, this happened once. And then they were able to do some fancy attribution. Why did I bother you by telling this story? Well, it's kind of cool, right? It's fun to tell stories about catching bad guys. Also, every piece of data we need to think about with that analytic mindset, that frame of mind. Be it trying to figure out if my 10-year-old is sneaking Minecraft again. Turns out we've got to hide the PS3 regularly. By regularly, I mean every 2 days. Or you got 1 trillion net flow records. Okay, back to the slide. Operationalize your discoveries. I've described using large piles of RAM to let data slam into itself to discover things. This is called interactive analysis. And in the Spark stack, this is one of the 3 types of engines that they build. They tend to put GraphX in there. Then this is a place, the next phase of developing an analytic is something that MapReduce does really, really well. Test it. You've got 1 trillion records. How many times does it occur? Is it statistically stable? Did you find a behavior that's repeatable that you're seeing happen over and over again? This is a bulk process that you don't care if it takes a minute, an hour, or a weekend. Now, you'll be a little annoyed it takes a month or so. The interactivity is not required there. And then you want to put it into an event stream processor. Spark streaming, Storm, a number of commercially available complex event processors that look specifically for this behavior at line rate. As dumb as it sounds, 40 gigabits a second isn't that fast if you know exactly the behavior you're looking for. There's only, what, 4 billion things on the internet, except for IPv6, okay? Which means with a sufficiently large pile of RAM and a very carefully written C++ representation, you could have a single sensor keep track of a set of behavior of the entire internet. Which means if you discover a behavior, now what I just said is not free to do, right? But it's possible. If you discover a behavior, you test it, you're not sitting on 40 gigs a second on your uplinks. Cool. Well, now you've got something to go look for. Plan for that cycle. My buddies with the 7 trillion records a year, they plan for knowing they were going to need to answer the questions. They know they don't have this stuff in place right now to do it. That's okay. They've got the data that supports search, that's letting them handle their bottom set of analytic problems so that the quick wins are happening, so that the decision makers realize that this story that we've been telling actually comes in 3 acts, and it's going to be a great blockbuster, and I'm going to cast the right people in it, all those nice things. But if you can't get through the first act, nobody's going to let you record the second one. So plan for the whole thing. So when you discover something, you're ready to operationalize it. And this last thing, use time to your advantage. This is a particular hobby horse of mine. Whatever is happening to you, with the possible exception of some fantastic ransomware, is not instantaneous. Everything has a wait phase in it. There are elements to that wait phase that talk about the beaconing periods or the callback periods to know when to go active. In queuing theory, we call this an Erlong. An Erlong tends to be the length of the interaction. And when you call up on the phone, because we still call on the phone to solve whatever problem the airline created for us, they use Erlongs to figure out how many operators they need to have based on call volume, all of that. Well, if you call the Erlong the same time period that the person doing whatever it is that's got the malware on your network wants as the responsiveness of whatever that activity is, they have to sample it half the Erlong to be able to pick it up and be responsive in that time. Which means there are now outer bounds for how frequently the beaconing or phone hum behavior has to be happening to catch the ongoing underlying effect. Cool. That means they can't be super stealthy and only phone home once every 3 months, unless the impact that they want to have, it has a 6-month window on it. That gives us a better fighting chance, which means that gives us more stability, more repetition to start finding clusters of things, to start saying, hey, what's that now? We've got plenty of math. We've got lots of cool computers. EC2 and other cloud service providers are making things, they cost money, but you can get a computer by clicking your mouse a couple times. What we don't have is enough people who think about the problems. And you say, what am I actually trying to answer? I got all the IDS alerts. Okay, why? I'm running this big blah, blah, blah instance. Okay. How is that furthering your security goal? If you want to get a hold of me, I'm local. Feel free to email or call. Email's better, but it's because, contrary to popular belief, I don't like talking that much. I'm going to stop now. You guys got any questions? Yes, sir.
So for a non-stance guy, where do you recommend just starting?
Yes. Where I started that was really helpful for me is a study in, and by the way, thank you everybody. I know I'm the last thing before lunch. I really appreciate y'all listening. So I started by studying what small sample size statistics was, and a really smart statistician told me it's about 13 to 15 elements in a data set. I studied the difference between, I studied something called bootstrapping. Bootstrapping is a way to take a small sample size data set and kind of estimate it larger so you can do more things with it when you don't have more than 15. I actually looked at numeric recipes in C because there are cogent explanations of things like chi-square similarity coefficients there. And then I read a bunch of Vern Paxton's papers. Vern is out of UC Berkeley, and he's been writing on this for 20 years, and he's got a really cogent description of why parametric methods, which is where you calculate some actual likelihoods, don't hold here. Vern is also, Bro is Vern's baby, and we use Bro heavily because it runs up to 40 gigabits a second, given the right conditions. It's a finite state machine under the covers, which means you can write arbitrary metadata extractors for it. It will give you paired level 5 netflow-like stuff natively, as well as, because it's a finite state machine, it does a lot of kind of really fancy behavioral analytic stuff and gives you great signal for doing these sorts of analyses. And if you want to, give me a call. I love just getting together and talking about nerdy math. More questions? Yes, sir.
Like, according to this model, you're saying that it doesn't make sense to use tools like Spark ML to do machine learning at scale?
No. What I'm saying is that use machine learning know the question you're asking before you start running it. So there's this thing called a Turing machine, which is this intellectual construct which says that this problem will eventually halt. I like to take it and say that there are analytic Turing machines, which is that there are analytic engines that possess sufficient mathematic operators or arithmetic operators, for all of my real crazy math homies in the crowd, that say that you can compute any piece of math that you need to using the operators present in the engine. Spark is one of those. MathML is a great place to start. I would encourage you to look at some of the DEF CON forensic puzzles as a place to get good data that has known badness in it so that you're doing machine learning over something interesting. Additionally, there's another interesting thing to think about. User agents are very descriptive. My iPhone, on average, and this was a few years ago, lets out 13 user agents on average over an hour. My MacBook does about 6 or 7. The reason that my iPhone is so many more is that every one of the apps has its own user agent. Now, using the apps themselves to do operating system prediction, that's an interesting ML problem. Now you might say, I know how to do it. Okay. I beat on it for 6 days in an environment where we had 1,300 devices on the network and 4,000 devices in the DHCP pool. That's an analytic problem. So I love Spark. We use it extensively. My perspective is know the question you're asking before you just start jumping into ML. More questions? Okay, there's one other thing I have to say. Do not file your taxes based on what I just said. Okay. Seriously, thank you very much. I've had a great time.